Greetings. So let's get started. With this session. So if you recall, we were dealing with frequency response, and frequency response has to do with the steady state output of the system when a sinusoidal input is given to the system, and we saw that for stable linear time invariant system, when we give a sinusoidal input, the steady state output is also a sinusoid of the same frequency, but scaled in magnitude and shifted in phase, right? So let's look at the visualization of the sinusoidal transfer function T of j omega using what is called as the Bode plot, because the magnitude of the input is scaled by the magnitude of T of j omega, and the phase of the input is shifted by the phase of the Planck transfer, the sinusoidal transfer function T of j. Okay. As we briefly discussed in the previous session, the Bode plot has two subplots. Okay. So the first plot essentially is the magnitude plot, wherein the magnitude of P of j omega is plotted in what is called as a decibel measure. Okay, we will see what this decibel measure is. Whereas the phase is plotted, not the phase, the frequency is plotted on the abscissa using a logarithmic scale. Okay, so we will see why a logarithmic scale. Okay, so what is this decibel measure? So this dB stands for decibel. Okay, so how do we get this decibel measure? We essentially take logarithm to the base 10 of this magnitude of P of j omega and multiply by 20. Okay, so that's what we call by a decibel measure. So essentially, let's say we are given some number, right? So the magnitude of P of j omega is going to be some real number, right? Isn't it? It's going to be a positive value, right? So if we have a positive value, what we do is that we take the logarithm to the base 10 and then multiply it by 20, okay, to get the decibel measure. So for example, if we take the number 1, right? If I take logarithm of 1, what will I get? What will be log of 1?
0.
It will be 0, right? So then 1 will correspond to 0 decibel, so on, right? So if I take log of 10, I will get 1. So 10 will correspond to 20 decibels because I have to multiply by 20 and so on, right? So we will see why we are using this unit for the magnitude, and what is this, a logarithmic scale, and why do we use a logarithmic scale? So suppose to understand that, first let's understand the linear scale. Suppose all of us are familiar with the linear scale. If I want to plot, let's say, a linear scale of frequency, what do? If I mark two successive markers, the difference between the two successive markers is going to be the same. So here I have plotted from 0 to 10, right? So we can immediately observe that if I am using a linear scale, if I subtract two equally spaced set of markers, okay, the difference is going to be the same. Okay, so we can immediately observe that if I subtract the values of 2 and 1 and 3 and 2, I will get the same value, right, which is 1. So that is a linear scale. That is an example of a linear scale. Now, if I were to have a logarithmic scale, let's say for frequency, what is this logarithmic scale? So imagine a scale where equally spaced markers have the same ratio, okay, when divided by one another. So let's say we start with 0.01, right, 0.1, right, 10 squared, 10 cube, and so on. Okay, so this is a logarithmic scale. Okay, so you can immediately see that in the logarithmic scale, what is happening if I divide the numbers associated with two equally spaced consecutive markers, right? Consecutive set of markers. the ratio is going to be the same. So here we can see that if I divide 0.1 by 0.01, I will get 10, right? If I divide 1 divided by 0.1, I will get 10 once again, right? So you can see that the ratio of two successive set of markers will be the same, right, in a logarithmic scale, right? So that's the fundamental difference between a linear scale and a logarithmic scale. Of course, here we are by in this discussion on what to say frequency response, we will be taking logarithm to the base 10. All right. So that's by default. So from here onwards, I will just write log. Log will mean it is logarithm to the base 10. Okay. So please remember that. All right. So once again, in a linear scale, if you take the difference between two successive markers, the difference is the same. Here in a logarithmic scale, you can see that the ratio, right? So that's a fundamental difference, right, between the linear scale and the logarithmic scale. Okay. So why we use a logarithmic scale? Because you can immediately see that we can plot a larger range of frequencies. Okay. Using a logarithmic scale, right? So I'm sure all of us can immediately observe that, right? So we can see that when we use a logarithmic scale, we are able to go from 0.01 to 10 power 3, whereas using a linear scale, in the example that I have plotted, like if you want to cover a larger range, we need a very large scale, right? So that is the difference, all right? So essentially, we have, this particular fundamental difference or fundamental advantage of the scale of interest. Okay, so logarithmic scale, we can plot a larger range of frequencies which will be of interest. See, for example, when we do, let's say, suspension analysis, ride analysis, and so on, right? In fact, if you look at standards such as ISO 2631, right? So they will say, okay, please evaluate vibration levels from 0.5 hertz to 80 hertz. So you can see that that's going to be a fairly large scale of frequency, right? So then, using a logarithmic scale, we can plot things very conveniently. All right. So that is one advantage. And another advantage is that we can expand low frequency regions. Okay. So we can expand the low frequency region. Okay, using the logarithmic scale. All right. So that is also an important advantage, okay, of using a log scale. All right. So what do I mean by expanding low frequency region? Because even if we look at the above plot, see, if I want to plot what to say 0.01, 0.1 and all in this what to say linear scale, you will see that I need to go very, very close to 0, right? So then the question becomes, how do I even visualize that? Right? It will become pretty challenging, right, to visualize that. On the other hand, I can easily visualize 0.01, 0.1, and so on, right, on the logarithmic scale. So I am expanding the low frequency. Okay, so these are a few reasons why we essentially use logarithmic scale for frequency. Okay, I hope the point is clear. Okay, some more definitions associated with this frequency range is that, like, we need to know what is 1 decade of frequency. So a decade of frequency covers a range from a frequency to either 10 times above it or 10 times below it. So what do I mean by this? So let us say I take a frequency omega and then I consider a region between omega and 10 times omega. Okay, so I am considering a range of frequency that is 1 decade above omega. Okay, So I hope it's clear why it's called 1 decade above. Okay? Decade means you multiply by a factor of 10. Okay, when you call it as above. So, but on the other hand, if we consider range 0.1 omega to omega, we are essentially dealing with a frequency range which is 1 decade below omega. Okay, so that is an alternative alternative or a complementary frequency, right? I hope it is clear what is meant by a decade of frequency, right? Similarly, we can have a frequency range which is in terms of octaves. So what is an octave? We go from a frequency to twice that frequency. So going from omega to 2 times omega will indicate a frequency which is 1 octave above. Okay. Similarly, going from a frequency which is half times the frequency to that frequency is going to be 1 octave below omega. Okay, so that's what is meant by a decade and an octave. Okay, so these are frequency ranges. All right. I hope this explains why we use a logarithmic scale, right, as far as the frequencies are concerned. All right. Now the question arises: why do we use a decibel measure? Okay, for the magnitude. So please note. See, as I mentioned, from here onwards, I will suppress the base 10. Okay, if I say log, it is logarithm to the base 10. Of course, if you take the natural logarithm, it is represented by ln. Okay, so when you want to calculate a logarithm to the base 10, like please don't press ln in your calculator. The ln will be logarithm to the, it will be the natural logarithm, right? So there is a difference between the two. Okay, so it's logarithm to the base e, right? So that's something which is very important, right? So now the question that arises: why do we have, why do we choose a logarithm or a decibel measure, right, for P of j? So why do we choose this a dB measure for the magnitude of P of j omega, the magnitude? So once again, a similar reason. Okay, we can have an expanded range because we are taking logarithm. We can go from very high values of magnitude of P of j omega to very small values. Okay, we can once again expand the low magnitude region, just like expanding the low frequency region. We can also expand the low magnitude region. Okay, and we can, another important advantage is that like we can plot individual factors and add them to get the composite plot. Okay, what do I mean by this? Okay, let me explain. What do I mean by that? Before I explain this, I should let's recap some fundamental quantities. So if I take log of a times b, it will be log of a times log of log of a plus log of b, right? So all of us are aware of this. As I mentioned, from here onwards, I will suppress to the base 10. It's understood that we are dealing with to the base 10. So log of a divided by b will be log of a minus log of b. Okay, so we are, all of us are aware of these what is representation, right? So now, if we apply this to the point and the study, so let's say P of s is going to be from k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn. Okay, so then what will happen is that like P of j omega is going to be equal to k times j omega plus z1 all the way till j omega plus zm, right, divided by j omega plus t1. Let me put parenthesis, all the way till j omega plus tn, right? So this is what I will have. Correct? Is it not? So now what will happen if I take the magnitude of p of j omega? If I take the if I convert the magnitude of p of j omega into decimal measures, let's not worry about multiplying by the what to say, factor, right? 20. So what can happen is that if I take the logarithm of this, please note that the magnitude of p of j omega is going to be equal to the magnitude of k multiplied by the magnitude of j omega plus z1. As we discussed, the magnitude of products and ratio is going to be the ratio of the individual magnitude, right? So products are ratios of the individual magnitude, right? So this is what we will have, okay, as the magnitude of the composite sinusoidal plant transfer function p of j omega. So let's say we take 20 log magnitude of p of j omega, right? So what will happen is that due to the property of logarithm, so we will have 20 log k plus 20 log j omega plus z1, right? The magnitude of j omega plus z1. We add all these things until 20 log magnitude of j omega plus zm. Then we will have 20 plus 20 log the magnitude of 1 by j omega plus t1. Of course, I can rewrite this as minus 20 log j omega plus magnitude of j omega plus t1, but I can write in this way also, plus all the way till 20 log 1 divided by j omega plus tn. That's nice. Okay, I hope it is clear, right? So now I hope it is clear how the third point becomes an advantage. So in other words, if we are able to rewrite the plant transfer function as a product of various lower order factors, right, in this manner, then what will happen is that we will be able, to plot the individual Bode plot, okay, of the which constitute the plant transfer function, right? And then we just add them, right, to get the magnitude plot. All right. So that is the advantage we have. All right. So I hope now it's clear why we use a decibel measure for the magnitude of p of j omega. The advantages are that once again, the decibel measure helps us to extend the range or expand the range of p of j, magnitude of p of j omega that we can plot. Second thing is that it will expand the low magnitude region. The third advantage is that we can plot the magnitude plot of the individual factors that make up the transfer function, and we can just add them. Okay, that's about it, right? Then we will be able to get the total magnitude plot, right, of the sinusoidal transfer function. All right. So now, if we move to the phase plot, we are going to get something similar, right? The phase of p of j omega, as we discussed, it's going to be just the sum of the individual factors, phases of the individual factors. So we are going to have a phase of k plus phase of j omega plus z1 all the way till the phase of j omega plus zm. Okay. And then plus the phase of 1 divided by j omega plus p1 all the way till the phase of 1 by j omega plus p. Of course, we can write the phase of 1 divided by j omega plus p1 as minus phase of j omega plus p1. Okay, the phase of a reciprocal is going to be the negative of the phase of the original factor. Okay, so that is something which is well known, right? So this is what we can once again see that by using these ideas, like we can essentially decompose, like the what to say, essentially we can essentially decompose the transfer function, like based on what are the individual constituent blocks, then we plot the phase diagram and the magnitude plot of the individual blocks, then we just add them. That's it. Like then we essentially get these things, right? So that's about it. Like, so we can immediately observe that we can very easily construct the Bode plot of any given transfer function in this manner. All right. So that is the idea. Okay. I hope that is clear. All right. Okay. So any questions in this regard till now? So once again, the Bode plot has two plots, two constituent plots, the magnitude plot and the phase plot. In the magnitude plot, of course, in both the plots, we plot the frequency using a logarithmic scale. The reason why we use a logarithmic scale is because we want to expand the low frequency region, and also we want to extend the range of frequencies that we can plot, right? And we use a decibel measure for the magnitude for the reasons that we just discussed, all right? So now, if you look at the phase plot, so we looked at the magnitude plot first. So if you look at the Bode plot, the first plot was the magnitude plot. Okay, so this was the magnitude plot. Okay, where we plotted the magnitude of P of j omega versus omega. All right. Some people will also call it as the log magnitude plot. Okay, so they mean the same thing. The reason why they call it as a log magnitude because the magnitude is plotted using a decibel measure, right, which involves taking the logarithm. So an alternative name that terminology that you will encounter is log magnitude plot, right? So for this particular diagram. So now going to the second plot, which is the phase plot, the Bode plot. So what happens in the phase plot? As far as the phase plot is concerned, we essentially plot the phase of P of j omega in degrees, okay? And this is frequency on the x-axis of the axis, right? So the phase of P of j omega in degrees is plotted using a linear scale. Of course, for omega, still a logarithmic scale is used on the x-axis. So linear scale is used even for the decibel measure, right, in the magnitude plot. Okay, so only the x-axis is plotted on the using a logarithmic scale. Okay, as far as the frequency is concerned. Okay, okay. So now now that we have looked at what are the two subplots, okay, involved in the Bode plot, namely the magnitude plot and the phase plot. The question that we ask ourselves, is the following, right? So we have immediately seen that one of the important advantages is that like we can break down, like the Bode plot as a product of certain fundamental building blocks, right? And we plot the magnitude and phase plots of those building blocks and then we add them, right? So that's it. Like we can immediately get the Bode plot of any given transfer function, right? So that's an advantage for us, right? So the question becomes, like how do we use this to our advantage? Okay. So the question that we are going to ask ourselves is that what are the building blocks that would help, okay, that form the constituents of any transfer function. Constituents of a transfer function. Right? So if we are able to answer this question, and if we are able to plot the Bode diagram for these Bode plot for these building blocks, then we are in a good shape, right? Is it not? Because we know how the Bode plots will look like, and then like we go forward. That's it. Okay. So what are the building blocks? The answer is the following. So if you look at any typical transfer function, we may have a constant scalar k. We may have an integral term 1 by s. We may have a derivative term s. We may have a first order term of the form 1 by ts plus 1, and then the reciprocal of that ts plus 1. We may have a second order term, because if we have complex conjugate roots, we can express that as a second order term of the form omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, and of course the reciprocal of this, right? So which will be s squared plus 2 zeta omega n s plus omega n squared divided by omega. Okay, so these are the various blocks. Okay, so if we are able to learn as to how to construct the Bode diagram or the Bode plot for these individual constituent blocks, then we are in good shape, because we would be then in a position to plot the Bode diagram for the other blocks, right, and add them, so that like we get the composite Bode diagram, right, of any given transfer function, right? So that's what we are going to learn over the next few classes. We will learn how to plot the Bode diagram, and then like we will so that like we learn how to plot the Bode plot for any given transfer, right? Okay. Of course, ultimately, in real life, what we will have is that like we will typically have the inverse problem. Okay, so when even when we do projects, we will see that we typically can get the Bode diagram from field experiments, right? Then we need to reverse engineer within code, right? The transfer function, right? So we solve the inverse problem, okay, when we go for field application. So that's also something we will discuss. Okay, as we go. All right. So any questions? Let me get started with the Bode diagram of the constant block today, and then like we will go further, okay, in the upcoming class. All right. Okay. So let me start off with the first block. So let's call this like some d of it, okay, so that like we don't confuse with other notation. So let's say we take the first block as k, okay, which is a scalar. So k is a real number. It can be positive or negative, right? So if we substitute s equals j omega, since k is a scalar, it won't change, right? It will remain k, right? Because there is no s here, right? As such. So what can I say about the magnitude of this d of j omega? It will be the absolute value of k. Please note that we need to convert it into decibel measure. So we write 20 log to the base 10 magnitude of k, okay, in decibel measure. Okay, so that's the way we write, okay, because that's the magnitude measure, right? So now if I have to calculate the phase, please note that the phase of k depends on the sign of k, right? So the phase of k is 0 degrees if k is less than 0, right? And I can have it as plus or minus 180 degrees depending on the way we interpret. If k is less than 0, right? If k is less than 0, it is going to lie on the negative real axis. That means the phase is going to be plus or minus 180 degrees. If k is on the positive, it is going to lie on the positive real axis. The phase is going to be 0 degrees. Okay. So if suppose if I want to plot the what to say as an example, right? Let's say k is equal to 10. Okay. If k is equal to 10, what will be the decibel measure? What do you think will be the magnitude? In decibels? What is the log of 10?
1.
1. Okay, then we multiply by 20. Okay, so what will the result be?
20 dB.
It will be 20, right? Okay, so you will see that this will be the log magnitude plot, right? So it will be a horizontal line at 20. In general, it will be 20 log to the 10 magnitude of k. Okay, this is in general. I just took a very particular example, right? That the magnitude of k is, the k was um, 10, and so we got the magnitude value as 20 decibels. So if I now want to plot the phase of this k, what will I have? What will be the phase of 10? It will be 0 degrees, right? Because it's a positive number, right? So please note that it's going to be on the positive real axis. So the phase is going to be 0 degrees, right? So consequently, it is going to be once again a horizontal line at 0, right? So that's how the magnitude plot and the phase plot, okay, of 10 would look like. Okay. So I hope it's clear how we got it. All right. Okay. In this manner, we are going to go and learn how to construct the Bode plot of the other remaining blocks. So what I will do is that I will stop here for this session. We will continue to learn how to plot the Bode plots of starting with the factor 1 by x, okay, in the next session. But one thing which is interesting that we will learn as we go along is that like there is going to be some symmetry, like between, let's say, the Bode plot of 1 by s and s. Okay? So if we know how to plot one, we know how to plot the other, right? Because 1 by s and s are reciprocal factors, right? So there is going to be some interesting symmetry or reflection over there, right? So as we will learn it as we go to that factor. All right? Okay. Fine. So any questions on what we have learned today? Okay. So if not, I'll stop this session here and then we'll continue the next.